Yeah. So welcome to our Ocean Data Factory webinar series. And today we will have Yanis share with us about combining citizen science and AI to predict HABs in the Baltic Sea. So the harmful algae blooms is a serious problem, and due to the climate change, we probably will going to see more and more such harmful algae blooms. Then how shall we cope with them? And how can citizen science and AI help us? And today our speaker is Yanis. He's a data scientist from Combine, the company Combine, and also an engineer with a background in actuarial science. He has a lot of experience in natural language processing, probabilistics, graphic models, and financial modeling. He has built scalable pipelines and machine learning deployments for deep learning analytics and commercial AI product development use cases. And his experience stretches from insurance and banking to telecommunication and water utilities. And he has strong interest in furthering the field of AI and using algorithmic problem solving to create lasting value. Yeah. And this project, I also would like to introduce Anna Chauhan, because she is really the expert, with harmful algae blooms and initiate all this citizen science work. So it's great that we can have these experts from different domains together to work on so important problems in this context of sustainability and climate change. So now, let's have Yanis share with us. And I'm very excited about these projects and the algorithms and all this the citizens' contributions. Yanis, please. Thank you.
Thank you, Yishin, for that introduction, and welcome everyone. I think for those of you familiar with ODF and who have been following the developments of our use cases, this will be a bit of an update on a use case that some of you might have heard of before, referred to by many names, including killer algae and the Algal Bloom Sweden project. So today I'd like to talk a bit about what we're doing in that project and especially how the last season has gone in terms of the development and the longer term kind of plan for this beyond this season. And so the title of this will be Combining Citizen Science and AI to Predict Harmful Algal Blooms in the Baltic Sea. For those of you who need a bit of an introduction very quickly, since I'm not the expert on this, the problem of harmful algal blooms really refers to these growing algae colonies, which basically grow out of control and potentially produce toxins and other hazardous things that affect human health, but also the health of the ecosystems around them. And on the top right here, you can kind of see how this process happens, which is mainly through this eutrophication. So we can see that there's agricultural and other sources from human-made waste, for example, that enters the ocean through nutrient runoff. And this lands both at the surface layer, but also then goes down into algal bloom form, and eventually also sinking and decay of algae, which then causes things like dead zones where species struggle to survive. And at the bottom right, you can see an actual example of this. So what they look like from a bird's eye or a satellite perspective. Quite beautiful, but also quite massive in scale, and yes, kind of like a cyclone on water, destroying many things in its path. And the reason why this is a problem is because these events are increasing both in frequency but also in magnitude. And what we've seen is that since the human component cannot be removed, the largest or the biggest goal we have at the moment is mitigation of this problem. And that's really the only option that we can strive for. And there's a lot of opportunity in terms of the data that's being collected out there. but there's a huge lack of actual tools and applications of this data to make it useful to both individuals out there, but also to industries and things that rely on this information about that are affecting their daily work as well. So why the Baltic Sea in particular? And this is because there's been, since the 1900s, a huge increase in this, as there has been in other places as well, but also that there's very little understanding of, you know, where this is going to go, how much it's going to increase in the coming years, but also how much of an impact this is going to have on the spread of, for example, these dead zones that we mentioned earlier. And this is kind of a way for us to understand the underlying effects of these changes in the environment on the species that inhabit the Baltic Sea. So that's why we focus clearly there. And that leads to the project, which is Anna's project, funded by Formas, which is called Tackling Harmful Algal Blooms, and focuses on the development of an innovative and integrative method of forecasting toxic cyanobacteria in a changing environment. And I think that's the focus here is also on the innovation part, but also largely on the changing environment. The idea that we need to be able to keep up with changes and adapt the system to these changes as we discover them. And that leads us to two big research questions when it comes to the problem of algal blooms in the Baltic Sea. And the first one that we try to focus on is, given that we are able to identify a harmful algal bloom event, can we then use machine learning to understand the causes of this fundamentally, the factors such as the environmental or ecological conditions that best explain the reasons for its occurrence in a specific area, as well as other things such as its strength and its localization. And then furthermore, in research question 2, when it comes to the actual user perspective, given that we have a specific location that we care about, for example, a beach or some tourism hotspot, can we understand the likelihood that the conditions will become ripe for a HAB in that area in, for example, a given time frame, a couple of days or a week? And this requires us to understand also the dynamics with which the blooms move through the water. And very roughly, this came down to a solution architecture which looks a bit like this. We tried to integrate as many data sources as possible, including primary sources, such as those collected by citizens, which we'll get to in a bit, but also external databases that are available, such as satellite data from Copernicus and others, and environmental layers. And combine this with high-performance computing environments where we can train algorithms, as well as particle tracking algorithms, such as the familiar or kind of widely used algorithm TrackMass, which allows us to forecast where particles will move. And for both of those research questions, we have some expected outcomes. The first one would be, given that we have a bloom, which is the class 1 kind of circle you see on the right, and a model that's able to get to that prediction, can the model actually go back and say that these attributes 1 to n are responsible for the bloom, or primarily responsible? Of course, it's not that easy to perfectly say that these factors are the contributing ones, but these could be the most important factors when assessing the likelihood, and that's kind of where we want to be. And in the second case, we'd like to have a probabilistic map where we can say that this area is likely to be hit by this bloom within a certain time frame with a given probability. So that's kind of what you see here, with the increased likelihood being shown in darker green here towards the coast. But the question then is, how do we get to this kind of solution? There are many roadblocks, including the fact that past efforts such as the HAB-risk app and others have failed to really raise awareness with local communities, as well as actually keep the interest up to maintain these tools. And that often requires a buy-in from regional authorities as well. So not just developing something because it's interesting for us, but also interacting with those who will be using the data and integrating it into their legacy systems is a very important stepping stone for us to become a real useful tool in the long term. We also think that starting off with smaller ideas where we can iterate over them is a much better approach than starting with this grandiose plan of building the perfect model that can explain everything. And we also focus on getting direct feedback, not simply as users of our system, but as actual contributors of our system. So we, in other words, wanted citizens to become involved from the very beginning. And this is what kind of led us to the idea of citizen science and the importance of citizen science in developing the system from the ground up. We started with the particular communities who would be interested in this, and that includes the sports fishing community. And here you can see some articles and a picture of Anna as well on how the fishing community has been able to contribute through their own interest information about the environment, such as temperature, salinity, but also photos, and also, much more in-depth information, such as DNA samples and chemical information. These were kind of the first target group, specifically because we knew they were already kind of out there collecting this data and very interested in being contributors to such a system. But then there's the broader public, the broader general public who simply need to be made aware of this, but who also, through regular contributions to regional authorities such as the Länsstyrelsen, every summer contribute to reporting and acquisition. And these things were already happening. So a very important target for us was to make our system compatible and integrated with what regional authorities are doing, both for reporting of the data, but also for managing that data, storing it, and also using it for analysis later on. And this is where our other large partner, Maranics, comes in. They develop these data acquisition and management tools, which includes a form for us to collect data, but also a database for us to access this data and analyze it afterwards. So these ingredients were key for us to start with the citizen science approach. And to go into details about how we collect this data then, here is an example, the screenshots from what this looks like. Typically, when a user comes in, they will find this screen in the beginning that says they would like to report a bloom. They need to provide information such as their telephone number, and then they get a link to a form, which is what you see on the right, where they can describe things such as when they saw this, where exactly, what color, and optionally qualitative information such as did they want to leave a comment. Then we also put increasing focus in the second round on collecting image information. And this is because of the machine learning component being directly affected by the amount of image data that we have. We really wanted to encourage users to submit more pictures if possible. Of course, they could still submit without pictures, but we wanted to strongly encourage this kind of behavior since it helps us greatly with our analysis. And then finally, having submitted this information, including the images, we then send this to the actual experts at the regional authority, who then see a different part of the form, which is more about validation, where they then say this data is of good enough quality to be submitted to the actual map where the observations can be viewed. And if we put this together, then this is how we thought about solving the problem from a machine learning perspective as well. We started with the inputs from this form tool. So this includes then the observations of citizen scientists verified by subject matter experts. And then using the database tool provided by Maranics, as well as the computing environment provided by the National Infrastructure for Computing, we were able to build a classification algorithm that takes images provided by users and predicts whether or not these are blooms. And this doesn't happen in a kind of 1-0 way, but we have thresholding where it says, okay, if it's above a certain likelihood, then we classify it as being a bloom. We also work with optimizations along the hardware level, which means that we make these models as small as possible so that they can actually work on mobile devices. And this is because we envision, as you see on the very right part, that this will run on mobile devices, mostly as a way to feedback to the users who have submitted us these pictures so that they can have instant access to an app that identifies blooms based on the images that they themselves take. We also do analytics on other parts of the data, including the qualitative comments, which is what you see in the word cloud here, and I'll speak about that again later on. But we also then keep track of this geospatially by looking at longitudinally, how many did we collect over time, how many of those were approved, and all these kinds of useful insights that we can extract from the geospatial information provided by users as well. Now we get a little bit more detailed, I think, into the second round of data collection. So we've done this now for 2 seasons, and this is a little bit of a quick overview of what we collected during the 2 seasons. And you'll notice that there is a slight decrease in collections from 2021 to 2022, which we largely ascribe to the fact that many people started traveling again this year after the pandemic, and a large number of people were simply not on the East Coast to take pictures anymore. But what we do appreciate and yeah, really see clearly is that people have submitted more photos this time. We've had a strong interest in groups consistently delivering kind of submissions to us, and we've also been able to more consistently monitor the contributions over the season. So it was a little bit more sporadic, I would say. Last year, we had very low contributions relatively in the beginning of the season last year, and then increasing. And this year it was more consistent. So here you can see what I mean by this. We had in 2021, we had kind of this very slow uptake of submissions. We're kind of peaking in July, as we did again this year. But here we had a much more consistent distribution of contributions throughout the year. And we suspect this is also because of the system, people being more aware of the system and how it works, but also that, yeah, people have been starting to report much more earlier this year. And also we've expanded where we collect these things to different regions. And that may also affect what we collect at the end. So here you can see at the bottom distribution, which previously was only Stockholm. We've now included other regions, including Bottniska Viken and Norrbotten. So now we have a larger spread in the Baltic, which potentially means that we're also looking at slightly different timeframes for when things are collected. But from a data collection point of view, this is kind of preferred to what we had before, since we now have a much more equal spread of data across the season. We also analyzed, as I mentioned, the comments, which I think was profoundly interesting from a qualitative point of view in the way that people describe things that they see. We find that this is a very useful tool for helping us develop the next round of kind of the form, the next version of whatever we're going to develop as an app for people to submit data, because we could also provide them with suggestions of what they should, for example, how they could describe things. Instead of leaving it open, we could now go ahead and choose these things like slimy and green, mess, or, you know, something paint-like, these things all help us to categorize what people are seeing in a much better way, so that we break down the language into very similar concepts that we can all then build on. I think that's been quite an interesting thing for us to look at, especially as we see people settling on very much the same terminology this year compared to last year, where it was kind of, all over the place and much longer descriptions of things. People have now settled on what they think are the important characteristics to describe, and that helps us as well with our analysis. But we did have our fair share of issues collecting data as well. And now I would like to only talk about the kind of submission part of it. And this is because we encourage people to submit photos, means that many people felt compelled to submit photos even when they were not particularly useful. And this adds another layer of complexity for us because we need to process that data. So we love having image data, but we also know that users, irrelevant data adds more work for us. And this is kind of what you see here at the bottom, that some people thought, okay, I should just add a screenshot, or maybe I should just take some picture of something around me, and that's kind of good enough because I've already described the bloom. And of course, from a reporting standpoint, and from what Länsstyrelsen wants on a map, that's kind of sufficient. But for us who need to go through this data, eventually this becomes a problem. So again, to us, this points out the importance of, in the next round, providing an actual example, so a visual guide that tells people this is exactly how we need the picture to be taken, and also provide now, thanks to these pictures, examples of what we don't want. So we have a lot of those. But I think these are very important for people to come to grips with. What is it that we want to focus on? So yeah, then in the larger scope, we had general kind of data problems as well. There is a extreme imbalance when it comes to the data we got, but this is kind of the bias in how we collect the data. We're focusing on harmful algal blooms, which means people are going out there, they're taking pictures of the blooms or what they think are blooms. Of course, they're not providing us with images of, regular ocean conditions. That's not interesting, but yet it's necessary for the model to not be too imbalanced in terms of what we train our model on. Otherwise, we provide a lot of these false positive conditions where anything that's basically slightly colored in the ocean provides us with a HAB classification. So this is something that we're actively working on. There's also a lack of, as we mentioned, standardization when it comes to images, not only in the cameras that are used, but also in whether it's landscape or a portrait, whether people are taking pictures from far away or close by, or all these kinds of weird things or artifacts or show up. We also see that clearly, geographically, we'd like to have a consistent spread along areas. We'd like people to be taking pictures at more or less the same spots. But we know that this is not simply viable at the moment unless we have a large enough group of people taking these pictures. We will have sporadically where some areas just aren't monitored, either because they're difficult to get to or we have nobody who lives in that area. These are trade-offs that we have to kind of work with as well. And then we have the irrelevant object problem, the Bart Simpson problem, I would call it. We have these weird things that show up, including things like boats, where people take pictures of marinas, which include the water. So there are areas that we do want, but then there's also artifacts that we don't care about so much, such as people's body parts and bridges and things like that. So these are things we need to take into account. So from a modeling approach, then we have to take care of these. And what we do in this case is we firstly resize all of the images that we get to the same scale. This reduces the kind of huge scale variation that we see. Luckily, we have sufficiently high resolution images to make sure that we don't lose. It's not like we're losing out on important details, and smartphones provide a sufficient resolution in most cases. We also, as I mentioned with the irrelevant objects, for example, if you can imagine bridges and boats in a large image, we try to crop out only a certain portion, and specifically the central portion of an image, which is most likely to contain water when people take images, so that we get rid of most of the irrelevant artifacts. Of course, not all of them, but we exclude those problems to a large extent. We also have a part of the pipeline which takes care of color range exclusions, and this has to do with irrelevant objects such as desks, or in other natural environments where we suddenly have many different colors in there. We expect the ocean to be fairly uniform in terms of color distribution. So anything beyond this uniform distribution, we kind of exclude as extreme values in our case. And then we have also a manual final check that I usually perform, which is to say, okay, given all these steps, we might still have one or two that are kind of in a gray area where we need to make a call. And then there was also the issue of control data, which we solved in this round using external data sources. In this case, stock footage from other sea regions that were collected. So basically these royalty-free databases that provide images of close-up water bodies. And these were used to augment the actual data. And we saw that this in itself provided a huge improvement in the model performance, simply because of this imbalance that I mentioned before. So these are all crucial stepping stones to get the model performance up. And what the model then sees after training this, which is a image classifier based on the convolutional neural network. Here we have one way of viewing what the model sees, which is called a grad cam. And here we can see that the areas which are highlighted, kind of like a heat map, show you where the model is making its decisions, or what the model is making its decisions based on primarily. And you can see that through these images, the model is focusing on the water, primarily the kind of beginning of the water's body, so the area that we kind of see closest to the shore. And you can see also that it's skillfully in the top left misses irrelevant things such as the rocks, boulders that are around there, but also it doesn't focus too much on what's going on outside. It focuses on these patterns in the shallow waters. And you can also see on the right-hand side that it doesn't always succeed at doing that. And you can see some of the complications introduced by irrelevant objects in the bottom right, where we have also a section of a bridge, and we have the shadow cast in the water by the bridge. And we can see that the model is focusing on the water, but it somehow takes the shadow to be an additional artifact. And that is problematic, because we shouldn't have any distinction here between the normal water in the sunlight and the water in the shadow area. So improvements are there, and especially if we look at the first iteration of what we had, which was plagued by this problem of false positives, the huge data imbalance. We now see an equalization of that to some extent, but we still see some artifacts of both the way that the data is collected, but also the range of data that's collected. So the conditions in which the data is collected. So just to kind of, I guess conclude on the seasonal outcomes, what we see as what we have achieved in this second round, which I think is quite a lot, is that we have worked closely with more regional authorities than before. So before we had worked with Stockholm, and now we are also working with Västerbotten, and that has been a very fruitful collaboration. We've managed to double the proportion of photos that we collected compared to the last season. We've also put the awareness out there. As I mentioned, this is a very important thing for us to keep the interest level high, especially given that we started this during a pandemic year where, yeah, it was very, very interesting then when everybody was at home and could easily contribute. But now we need to make sure that it's still rewarding to contribute. And that includes working closely with local communities on the East Coast. And Frida, who is here, has also been instrumental in that process. So we continue to focus as much on the community as we do on the technical development side. I think that is what's paid off for us in this iteration. And then also when we look at the technical perspective, we see from the model kind of focus distribution, as you saw, that's improving, but also overall when it comes to the accuracy and the output of this model, we are reaching good levels, 0.8. So we are getting to a place where the model is making fewer and fewer misclassifications of actual HAB events and is able to recall a lot of the actual events based on those expert verifications. So this is becoming ripe now for a position where we can start putting this out back to users. And also, speaking of outputs, we have now released these two data sets, both the one for the first season and the one for this season on Zenodo in open source database there on Zenodo, as well as the Swedish National Data Service, which means that these data sets are now created in a fair way and are openly available to anyone for further research and investigation if they'd like to look closely at what we've collected, as well as full metadata descriptions and all those lovely things that make them easily usable to others as well. So this is an important part of what we, as we see our project's role inside of the larger ODF community as well, is to keep on delivering these products that can be used by a larger group and not just those sitting in the Algal Blooms Sweden group. And then what does the next season look like? Well, I think you could kind of expect a couple of these things. The first one is that we want to improve the UI. The data collection process needs to be refined in many ways, including, as we mentioned, this visual guide, telling people, here's an example of how you should take it, maybe providing them with kind of yes/no questions so that we can lead them to a specific description. We also want to collect more control data. So this involves, again, a strong connection to the community who's regularly in these locations and can take these pictures at regular intervals so we can use them to train the models and even out this distribution. What we've done now is use external data, but we'd like that to become completely internally generated data, because that is what's most relevant to the Baltic Sea and will ultimately help us produce better models. We also want to feed back to the users who've contributed with a first mobile app version, and we are very close to kind of getting there since the model is complete. The part that's needed in the beginning of the next season or the next year is going to be this integration part. How do we get this model into a nice, simple app to start, where users can just get this kind of probabilistic feedback? Yeah, it's probably not, because then it allows us to also then iterate, as we mentioned, quickly based on what they give us. And then, yeah, largely from this, we'd like to expand into those larger research questions, right, that I started with, which is, you know, now that we're able to identify HABs, how can we link this to the causal effects, right? How can we understand the underlying causes of this in a better way? And that means incorporating other data sources, not just the visual ones, but also environmental data that we get from layers in Copernicus, eModNet, those kind of things, including, you know, turbidity, salinity, all these things, current information, but also information from our local community, including those collecting data using their own vessels and things that they have regularly out in the Baltic. We've managed to even find those who are very excited about contributing this data that they collect live for other purposes, but which we could integrate into our models and make them kind of more real-time, fed with real-time data instead of only historical data. So these are both very, very exciting prospects for us. And there's a clear path forward, I would say, for the next version of this. And we expect the progress to be exponential given the things that we've driven forward up to this point. Yeah, this is again in how we envision the improvement of the data collection tool. It's not that important, kind of the details of every piece, but the idea is that we want to give back to users and use what we get from the users to simplify and improve every single component of this reporting system. And that now includes the app that's going to predict the blooms. So yeah, there's a lot of detail that's possible there, but the idea is that we want to give back to the users as quickly as possible and iterate. And that is it from my side. Thank you so much for listening. And I would also like to say that since this is an ongoing project and many of the people in the project are here, that if you'd like to contribute or get involved or just find out what we're doing and how you can get access to the forum or the app or all these other things and keep track of what we're doing, please get in touch with us. Also head to the Facebook page, which is Algal Blooms Sweden. And of course, we also are listed on the Ocean Data Factory website if you'd like to read about what we're doing within that context as well. And with that, thank you very much.